Hello. Today what I want to do is discuss kinematics and polar coordinates. So what we had done last time was in the last few lectures, we had discussed kinematics. We did so using vectors, but we did this in the Cartesian coordinates, right? We did this in the Cartesian coordinate system. So what I want to do today is discuss kinematics, but this time using polar coordinates. And polar coordinates work very differently in comparison to vectors. So let me just start off by explaining what polar coordinates are. I think you already know this. I'll just give a quick recap. So what we do is that we start off with this with a circle. This circle would be our starting point. So here we have a circle, and what we do is that we take any particular point. Let's say this point is x comma y in Cartesian coordinates. So everything in red is in Cartesian coordinates. All right, so let me just write that down. Red Cartesian coordinates. So these are the usual rectangular coordinates that we work with, and with green I will draw in polar coordinates. All right. So the way we deal with polar coordinates is that if I'm given any particular point, I can also describe it by, say, some a line connecting the point x comma y of, say, length r, which rotates anticlockwise through an angle theta. So in polar coordinates, I can write this as r comma theta. All right. So now, the reason the circle here is kind of important is because uh, looking at it as a circle allows us to see many things. In particular, it allows us to derive relationship between the Cartesian coordinates and polar coordinates, and that's pretty easy to do because this length over here is x, and if you notice, there is a triangle that is formed here, that is a right angle triangle, and using this relationship I can write that x equals r times cos theta, and similarly I can write that y equals r times sine theta, right? So now there's a couple remarks that I do want to make about this. In particular, in Cartesian coordinates, what we have is a vector, right? Here, even though r may seem like a vector, it is uh, at least yet it's not a vector. Here, this small r that I've denoted here, this is a scalar quantity. This is a real number, a positive, non-negative real number. It could be zero as well, and we are going to be using this as a to mean distance from the origin. We are not using r yet to mean a vector, a position vector. All right. Although, if we wanted, we could. So, if we wanted to write the position vector, we could do so in terms of the Cartesian coordinate as xi hat plus yj hat. And if we wanted to write a vector in polar coordinates, how would we do that? Well, what we do is that we introduce a small vector over here called r cap. And this r cap is what we call the radial unit vector. What radial unit vector does is that it will point in the direction that the particle is in, it is such that the r vector can be described as the magnitude r times the position vector r cap, the radial unit vector r cap. So essentially, this r cap always points in the same. It has the same direction as that of the position vector, the r, except that it is a unit length, and this actually turns out to be pretty useful, as we will see. A key difference to note here is that as position changes, let's say instead I were to end up here, then my radial unit vector will also change. But the I cap and J cap, they do not change. It is in this sense that polar coordinates are fundamentally different from the Cartesian coordinates, because in Cartesian coordinates we start off with two fixed vectors, I cap and j cap, and we define everything in terms of them. But polar coordinates, on the other hand, they are not coordinates in the same sense that Cartesian coordinates are. They are coordinates in the sense that using these two quantities we can describe a point uniquely, but there is no fundamental unit that we can use to describe every single point, because at the end of the day the vector r cap is defined in terms of r, which in turn is defined in terms of I and j cap. So polar coordinates in this sense is just Cartesian coordinates in disguise, but at least it may seem like it, but that's not entirely the case. It's just that the nature of the way we are dealing with vectors here is entirely different, right? So even though polar coordinates allow us to approach the problem in a different way, fundamentally they do not represent a new coordinate system in the same sense that Cartesian coordinates do. What I mean by that is, more technically, Cartesian coordinates I cap and j cap form what is called a vector space, but r cap does not allow us to do that. Uh, Additionally, if you notice one more thing, is that we are able to describe uh, position vector using just a single coordinate, using a single unit vector, right? R cap. Whereas in Cartesian coordinates, we require two different unit vectors, I cap and j cap. And we know this makes sense in Cartesian coordinates, right? Because in a two-dimensional system, you need two different vectors, two different unit vectors, which we call basis vectors. But in polar coordinates, we don't really need those, because we are using two scalar quantities to associate, which we associate with a point. So there are some these technical differences between polar coordinates and Cartesian coordinates, but for the most part, we these would not be relevant to us, because when you're solving problems, it kind of becomes somewhat irrelevant. Regardless, these nuances are worth mentioning. Right. Uh, Now, another thing is that one more thing to notice here is that whatever this what this position vector is, the radial unit vector, it depends on the position vector as I mentioned before, but it is also a function of theta, right? So I did not write that here, but more explicitly stating it, this is actually a function of theta, because as the position function varies, uh, the as the position function varies, we we will be changing the radial unit vector as theta changes. So the radial unit vector itself is a function of something else. So it is again not fixed in the same way that I cap and j cap are. And of course, r could also be subject to change in terms of theta. So in Cartesian coordinates, the y is the dependent coordinate and x is the independent coordinate. In polar coordinates, r is the dependent coordinate and theta is the independent coordinate. All right. Now, can we find what theta is? So, what I would like to do is have another vector that acts as uh, vector perpendicular to r cap, right? So this would actually be simplify things a lot for us, and this vector is what we call theta cap. All right. And well, the relationship between theta cap and r cap is pretty simple. We want them to be perpendicular, and this extra vector will actually help us define many new quantities and look at things a little differently, simplify mathematics for us. But strictly speaking, we do not need theta cap to describe the position vector. Okay, so what is this theta cap? Well, notice that the vector r cap is perpendicular to the vector theta cap, and the vector r cap is given by cos theta I hat plus sine theta j hat. How do I know this? It's because, well, the position vector r is given as xi hat, which is again r cos theta I hat plus yj hat, which is r sine theta j hat, where I'm using these two to arrive at this. And then I can factor out r and write it as cos theta I hat plus sine theta j hat, and this is exactly my r hat vector, right? So we have r hat described as cos theta I hat plus sine theta j hat, and if theta hat is perpendicular to this, essentially let's call it ai hat plus bj hat, then because these two are perpendicular, we can take the dot product, and what we would end up with is a cos theta plus b sine theta is equal to 0. We can simplify this, and by simplify we can rearrange this and get that a divided by b is equal to minus sine theta by cos theta. So clearly, any choice, uh, we want we have one of the restrictions here, that a by b is in this particular ratio, but another restriction on a and b is provided by the condition that theta hat, the magnitude of theta hat is equal to 1, which means that a squared plus b squared is equal to 1, right? A squared plus b squared is equal to 1 squared, which is equal to 1, right? So what I'm going to do is I'm going to use this equation and this equation to solve for a and b. So firstly I'm going to divide this by b squared, so I would get that a by b squared plus 1 is equal to 1 by b squared, and when we substitute this quantity here, we get minus sine theta by cos theta squared plus 1 is equal to 1 by b squared, which if we were to simplify, we get sine squared theta plus sine squared theta divided by cos squared theta plus 1 is equal to 1 by b squared. But now notice that if I were to make the common denominator, then over here I can write it as cos squared theta, and this becomes a common denominator. The cos squared theta becomes a common denominator, and the numerator would then be just 1, right? So we get 1 by cos squared theta is equal to 1 by b squared. So we can say that b is equal to cos theta. And similarly, we can solve for a, and we get that a is equal to minus sine theta. So solving this, putting everything together, we have that theta cap is equal to minus sine theta I hat plus cos theta j hat. All right. And for comparison, r hat was cos theta I hat plus sine theta j hat. And as you can check, both of them have magnitude of 1, and they are indeed perpendicular to each other, right? So these are the fundamental unit vectors that we'll be dealing with. Even though we do not need theta cap to describe position, theta cap is still quite important in some other ways. In the sense that when we are describing motion, we using polar coordinates will be able to separate it in the direction of the position and a direction that is perpendicular to position. This would be especially important when we deal with something called central forces, which we'll get to probably in the next class, right? So we'll cover that in the next class, and that this would be pretty important. Now, another thing that we need to know is we have established that r hat and theta hat are functions of they change with time. These unit vectors, they do not stay constant. So we would like to know how they change in time, right? Well, that's actually pretty easy to do. So what we'd like to do is we would like to evaluate dr hat d theta, dr hat dt, which would be equal to d by dt of cos theta I hat plus sine theta j hat. And how do we evaluate this? Well, the thing is that you don't need to be firstly, you don't need to be scared about having vectors inside differentiation. Differentiation with vectors works exactly the same as it does with scalars, except that you just have to be mindful of the order in which the vectors appear. So all the other rules, the product rules and everything, they work exactly the same. Okay. And when we differentiate this, first we would get that the derivative of cos theta, we would get d cos theta by dt times I cap plus d sine theta dt times j hat. And now d cos theta dt, that would be, well, the derivative of cos theta with respect to time, that is minus sine theta multiplied by theta dot, or d theta dt, right? We need to use the chain rule here, plus cos theta d theta dt times j hat. And once we have this, we can notice that we can factor out d theta dt. And from now on, whenever we are taking time derivative, we'll denote it with a dot on top. It's a shorthand way so that we don't have to write all d theta dt all the time. And theta dot will always represent d theta dt, and for that matter, not just theta dot but x dot or y dot will also represent that. Okay. So dr dt, dr cap dt would be equal to minus sine theta I hat plus cos theta j hat multiplied by theta dot. But this is exactly the unit vector theta hat, isn't it? So we get theta dot times theta cap, right? So this is the derivative of the unit vector r hat, and this would be very important to us. Similarly, we can differentiate d theta cap dt, and you will find that this is equal to minus theta dot times r hat. Right, so I'll suggest that you do it as an exercise. It's not very difficult, it's just straightforward differentiation. Right. So I'm just going to box these two equations because these are very important equations for us. These are equations that we'll see frequently in what's to follow. Right. Now, once we have a way to describe the derivatives, what we can do is we can talk about how velocity and acceleration behaves in each of these in polar coordinates, right? So, what we're going to do is that let's try to calculate what velocity would be. Velocity would be the time derivative of the position vector, right? But the position vector is nothing but the magnitude r times r cap. So we will now differentiate this, right? And differentiate this is pretty easy. We just use the product rule. So first we'll differentiate dr dt multiplied by r hat plus r times dr cap dt. Right, now dr dt is just r dot times r hat plus now the r will stay here, but dr cap dt would be equal to theta dot times theta cap, right? So we can write this again as r dot r cap plus r theta dot times theta cap. Now, now what does this tell us? Well, I'll sketch a small picture to help you understand what is going on here. Now, we have a particle that is here, right? Let's say that my particle is over here, and this is my position vector r like this. Now, what is happening is that I have r cap direction, and the rate of change of my position in that direction is given by r dot. In other words, it's telling us that the derivative of r with respect to time is exactly how fast the velocity changes in the direction of the position. But simultaneously, we also have another term to look here, which is in the direction of theta cap, right? And so I'll draw it like this here. This would be theta cap. Again, this is not to scale, but all right, yeah. What is happening in theta cap direction is that it's saying that you take the r and multiply it with how fast theta is changing with respect to time, and that is the amount in which the velocity will change in the direction of theta cap, right? So, in other words, the moment we start considering polar coordinates, we are faced with something that we didn't realize before, that we didn't see as explicitly before in Cartesian coordinates, which is that uh, velocity is changing in the direction of motion, but also in the direction perpendicular to motion, depending on how the motion takes place. What I mean by that is, in the situation that the motion takes place in a straight line and there is no uh, theta dot, right? If motion takes place in a straight line, then theta is constant, which would mean that theta dot is non-existent. In that case, this last term would vanish, and the particle will just keep on moving in a single place, in a single along a single line, right? On the other hand, uh, if the if it happens that the magnitude of the particle of the position doesn't change over time, then I only have the theta hat component to deal with, and that would give me a familiar case of the circular motion, right? So this is why what we do is that we divide this. We call them. We have these special names for these, and this component of the velocity would be called the radial velocity, and radial velocity is when theta is constant and r varies, um, whereas the other component, this part, is what we call tangential velocity, right? And this quantity r theta dot has come up again and again, so it turns out it's useful to give it a name. And this tangential velocity is also what we call, sometimes referred to as angular velocity, right? Because it's telling us how fast the angle is changing, right? And we denote it by omega. So in other words, omega is equal to r theta dot. All right. Um, oh, sorry. We Omega is just d theta dt, and if we want the velocity of the particle in a circular motion, then it becomes r omega, right? So this the theta dot component, angular velocity, is what we call as theta dot, right? Because that is that is the driving factor behind how the tangential velocity is behaving. So this angular velocity is known as theta dot, right? Now, there are plenty of examples that are given in the textbook that I'll refer to, and I would advise you to study through those examples. But an important thing to keep in mind is that, well, rather, an important new definitions here that we encounter, I'll list them down. So theta is what we call angular position, right? Theta dot is what we call angular velocity, right? Now, one thing to keep in mind is that theta dot is also sometimes denoted as omega, and theta double dot, that is second time derivative of theta, angular position, is what we call angular acceleration, right? And this angular acceleration is often denoted by alpha. And all of these things would be important to us when we do rotational motion. So these are some important quantities that we will meet again and again. But right now, what we have obtained is a complete description of the velocity, right? So what I would like to do is extend this same analysis that we did for the velocity vector towards uh, the acceleration vector, right? So the way we are going to do that is we'll define another, we will repeat the same process, right? So dv dt, which means d by dt of r dot r hat plus r theta dot times theta cap. And of course, we are going to have a lot of terms here, but each of those terms will tell us something about the acceleration. All right. So Well, let's start by differentiating the first term. By differentiating the first term, we will first differentiate r hat, right? R dot r hat. So we would get r double dot times r hat plus r dot times dr hat dt. And now, to differentiate the second term, we first will have to differentiate r theta dot uh, multiplied by theta cap plus r theta dot multiplied by d theta cap dt. And if we were to now simplify this, we get r double dot r hat plus r dot. Now dr cap dt is equal to theta dot times theta cap. We saw that before. Now, what would be r theta dot, the derivative of r theta dot? Well, that is just going to be r dot theta dot plus r theta double dot, right? Again, I'm just using the chain rule here, the product rule here, right? And then multiplied by theta cap, and r theta dot is r theta dot multiplied by d theta cap would be equal to minus theta dot times r hat, right? And if we were to combine all the terms, then we would end up with something that looks like this: r double dot minus r theta dot squared r cap plus 2r dot theta dot plus r theta double dot times theta cap. So we already have a lot of terms here that we haven't encountered before. Some of which we have seen before, but many we haven't. So let's take a look at them one by one. So r dot, of course, this is just the radial acceleration, right? This is just the radial acceleration. We are familiar with this, and this particular term, this is something that we have encountered before in terms of what we know as centripetal acceleration, right? This is what we have encountered before. Now, so both of these together are what they form our total radial acceleration, right? So this is not radial, sorry, this is a linear acceleration, and both of them combined give rise to what we call radial acceleration. And now we are only left to deal with the tangential components, right? Now, the term r theta double dot, this is something that comes from the acceleration. This is the acceleration that comes from changing the tangential speed, right? So this is just omega dot, right? So I mean, this is not omega dot. So theta double dot is omega dot, but r theta double dot, this is the acceleration that's coming from changing the angular position or changing the theta. So this is just r omega dot, or as we can otherwise refer to it as r alpha. And then this particular term is something that we haven't seen before, and this is what's called the Coriolis force. And essentially, this force acts in most places. Wherever theta and r are both changing, this force will always be there. And this is a fictitious force in the sense that it appears in the rotating coordinate systems. This is not a real force. So I hope you're aware of what fictitious forces are from Newton's laws. And this will play an important part when we're dealing with rotating coordinate systems, because in rotating coordinate systems, both r hat and both r dot and theta dot are present. So when that happens, the Coriolis force is active. A very important example of such a coordinate system is, of course, the Earth. Earth is rotating. So whenever we do any physics in the real world, at a larger scale, at a planetary scale, we have to account for the Coriolis force. So both of these together, they give rise to tangential acceleration. Right. So this completes our analysis of uh, kinematics in polar coordinates. But regardless, there's of course you will only understand this better if you work through some problems and go through some examples. For the most part, this is just like working in another coordinate system, except that I mean, you just need to get used to the notation change, but all the mathematics is pretty much the same as we did in the kinematics before. We're just re-deriving all of that mathematics for the case of uh, polar coordinates. So, yeah, now I would recommend going through the book by Klepner and Kolenkow. The Klepner and Kolenkow, they have a book called Intro to Mechanics, and this book is really good, and it's a good introduction. Chapter one of this book should be a good resource to go through these things. It has much more material also on vector kinematics and on how the derivatives of vectors work, which should be a good read, a necessary read. So it's a pretty easy chapter, and it has many questions. You could go through quite a few of them. What I love about it is that it has a lot of really good examples that they have worked out. All right. So yeah, let me know if you have any doubts.